Hello everyone and welcome to our Summit presentation. We're Team FarSounder and our project is called Network Control Signaling Precise Timing Control via Ethernet. Our technical directors are Matthew Coolidge and Matthew Zimmerman. Both are URI alumni. My name is Scott Brennan and I'm an electrical engineering major, and my partner is computer engineering major Justin Hall. FarSounder is a Rhode Island-based company that's dedicated to continual innovation in the field of marine navigation electronics for both private and commercial ships. FarSounder specializes in the development and manufacturing of 3D forward-looking sonar systems for marine vessels. FarSounder systems show what lies ahead in real time and also provide local history mapping, meaning a map is generated from all places previously traveled. FarSounder's sonar system consists of three main components: the transducer module, the power module, and the custom cable bundle. The transducer module is located in the water and houses the data collection system. The power module is located on board and houses the transmit system electronics. The custom bundled cable connects the two modules together and allows them to both send and receive data. The custom bundled cable serves many important purposes. It transmits a sonar pulse, triggers data collection to start and stop, transmits data from received sonar pulses, and sends power to the transducer module. The problem with FarSounder's current custom bundled cable is that it's expensive, heavy, and has a large bend radius, making it difficult to install and difficult to transport. FarSounder's current custom bundled cable contains one wire for a transmit signal, shown in yellow, two power supply conductors, shown in green, four digital in and out conductors, shown in red, and an Ethernet cable, shown in blue. FarSounder believed it was possible to use the already existing Ethernet cable to replace the function of the four digital in and out conductors, removing them entirely. The four digital in and out conductors serve the purpose of synchronizing the transducer module with the power module. Our belief was that we could use an Ethernet-based timing protocol known as IEEE 1588 to serve this purpose. IEEE Protocol 1588, also known as Precise Time Protocol, or PTP, works by setting up one device as a master clock and the other device as a slave clock. The master clock constantly reminds the slave clock of the current time with little delay, keeping the devices synchronized. Our ABO is to have successfully produced a sample source code for the development boards that meets FarSounder's requirements and can be used as a reference design by FarSounder for implementation in a future version of their electronics. This solution will be an entirely Ethernet-based method to synchronize the transducer module and the power module. By implementing this method, FarSounder should be able to remove the four digital in and out conductors from their custom bundled cable.
Throughout the course of our work, many technical accomplishments were made as a team. We laid the foundation for our development by identifying a hardware platform that supports the Precision Time Protocol, which can be used to synchronize device clocks to within nanoseconds of offset. We were also able to effectively demonstrate the Ethernet-based clock synchronization by porting the PTBD application to MCU Expresso, running the protocol, and indicating synchronization by controlling an LED via GPIO. The completion of our anticipated best outcome implies several economic benefits for FarSounder. Since the timing implementation can remove the need for dedicated digital I/O conductors, the cable connecting the power module and transducer module can effectively be shrunk. This results in a reduced cable size, weight, and manufacturing costs. Furthermore, it means that being able to use more off-the-shelf components and greater ease of installation. Through all of these benefits, we estimate that the cost savings for FarSounder would be about $300 to $400 per sonar unit. This block diagram showcases how FarSounder's data collection process begins in its current state and how it will ideally work in the future with our timing implementation. Currently, the sonar system uses the dedicated conductors in the cable bundle in order to signal the beginning of data collection and sonar pulsing. Because this transmission is instantaneous, the power module and transducer module are synchronized from the start. With the lack of dedicated trigger conductors, we then need a way for the transducer module and power module to agree on when the data collection happens. This is where the implementation of the timing protocol comes in. It allows the triggering of data collection to be sent via Ethernet to both devices, and because both devices are actively synchronized, they are able to accurately timestamp the data collection.
For my individual technical contributions, I first researched several microcontroller contenders and compared them in a spreadsheet. We used the spreadsheet to compare several microcontroller contenders based on their specifications and select the one that best suits our needs. I also successfully tested PTP implementation and local network communication between a PC and a microcontroller. This was the first step in setting up PTP between two microcontrollers. I also experimented with using one board as a master and one board as a slave. This was in preparation for setting up PTP on both microcontrollers. I learned about the file structure for projects in our IDE, MCU Expresso, and an alternate IDE, IAR Embedded Workbench. This was necessary to begin importing an important PTP demo project from IAR EW into MCU Expresso. I then helped migrate the AN12149 demo into MCU Expresso. This was a critical part in achieving our anticipated best outcome. After successfully importing the demo project into MCU Expresso, I then helped set up the microcontrollers to serve their respective functions. I verified that the boards were synchronizing properly by setting them up for oscilloscope readings. I then used the oscilloscope to provide visual proof that the synchronization process was working properly. From here, I programmed the board to activate an LED using the board's GPIO capabilities. I used the LED to indicate when the boards have achieved sufficient synchronization, which FarSounder determined to be a delay of less than 10 microseconds.
Between Scott and I, many technical accomplishments have been made. Some of my contributions include identifying methods of peripheral communications with other devices involved in the Sonar system, selecting a microcontroller evaluation board, and helping achieve operation of the precise timing protocol in MCU Expresso. I also helped to verify synchronization results, gathering performance data, and documenting our process for further development by FarSounder's team. When working to identify a suitable platform for development, there were some important things to consider. We needed to know if our platform has the features and capabilities to efficiently integrate into FarSounder's products. Some features we looked for included Ethernet, direct memory access support, and sufficient GPIO for driving external devices. Finding a device that was both affordable and full of the features we had been looking for took some time. We ultimately ended up with NXP's IMX RT1060 ARM-based microcontroller. Successful operation of the timing protocol was one of the more difficult challenges that we faced. The PTP-D application is written in C for use with the IAR Embedded Workbench IDE. This meant that it needed to be ported for use with our boards and the MCU Expresso IDE. This involved changing the configuration and directory structure of the whole project, which was achieved through much trial and error. Ultimately, we were able to get the application functioning on our boards from within MCU Expresso. Once we had the program running, it was then necessary to gather performance data to see if the protocol and application meets our timing requirements. We were able to determine statistics such as CPU load imposed by the application, network throughput of around 5.8 kilobits per second, as well as the effects of other devices present on the network in which the timing protocol will be taking place. In summary, we have ultimately achieved our anticipated best outcome of implementing an Ethernet-based method of clock synchronization for use in FarSounder's Sonar products. 2 IMX RT1060 evaluation boards are able to boot from onboard flash, begin running the PTP-D application, and effectively synchronize their clocks. This synchronization can be visualized via LED output on the slave device once it has reached an offset of under 10 microseconds. Once again, we'd like to thank all of those involved in helping our project become a reality. Thank you to both Matthew Coolidge and Matthew Zimmerman for their insight and technical assistance throughout this process. We couldn't have done this without you guys. Also, we'd like to thank Dr. Sunak for providing us with an amazing opportunity to gain some real-world experience in the world of electrical and computer engineering.